This is section 1.5, infinite limits. All right, so we've been dealing with limits up till now that had a particular characteristic which I didn't really tell you much about at the time, but we didn't involve infinity, at least not yet. So now we're going to involve infinity in our limits. So let's look at, say, this function. If you look at a table of values for this function as x approaches 2, both from the left and from the right, so make this table. Go ahead and do that, unless you see it there printed. I can't remember if this got printed in the notes or not. But use numbers like 1.5 and 1.9 and 1.99 and 1.999 to approach x from the left, and use numbers like 2.5, 2.1, 2.01, 2.001 as you approach 2 from the right. And from the left, the f of x values are just going as far in the negative direction as you can. Well, I was about to write an example, but it's really going towards negative infinity. Those answers, the closer x is to 2 on the left side, the further away. Like the answers for the numbers I gave you were -6, -30, -300, -3000. That's what's going on. On the right side, as x approaches 2 from the right, the function outputs are bigger and bigger and bigger, so they're headed towards positive infinity. So from a numerical approach, we're getting infinite answers, unbounded answers. If we look at the graph of this function, of course it has a vertical asymptote at x equals -2. I'm sorry, at x equals 2, pardon me. And the graph looks like this on the left side of 2. Notice those y values are headed toward negative infinity. They're going down without bound. The closer you get to 2, the further down it goes. And then the graph on the right side looks like this. So as you approach 2 from the right, those x values are just going up without bound. The closer you get to 2 from the right side, the higher up the answer is. And so what that implies for us then is that the limit as x approaches 2 from the left for this function is negative infinity. Now, that's graphical information. That's telling me that the y values are unbounded in the negative direction. It's also true to say that the limit doesn't exist because infinity or negative infinity is not a real number. So it's true to say that it doesn't exist, but saying that that one-sided limit is negative infinity implies something graphically that I don't want to lose. So I'm going to ask if the answer is negative or positive infinity. I'd much rather you tell me that because it gives me graphical information and not that it doesn't exist. Not that that's a false statement, it's just not as informative to say the limit doesn't exist in this case. So I'm going to ask that you do that with these limits that have an infinite or negative infinite result. And so we would say for the same function, the limit as x approaches 2, this time from the right side, we would say that that's infinity. And again, it's valid to say it doesn't exist, but I'd really rather see infinity, which means that the graph goes up, up, up as you approach 2 from the right-hand side. Okay. It's a convenient symbol that we're going to use to describe this unbounded condition, that it keeps going up or keeps going down forever. And this is called an infinite limit. And so if you look at the definition of infinite limits, let f be a function defined at every real number in some interval containing c except perhaps at c itself. the statement that the limit as x approaches c of f of x is infinity, and the limit as x approaches c of f of x equals negative infinity means something very specific that I don't really want to get into. It involves using delta, that crazy looking thing. It looks sort of like a scripty, scrolly kind of D. It's not, it's a Greek letter delta lowercase. And all that, it's all true. It just means the closer you get to 2 in this case, the further up or further down the graph is going. Now, if I asked you, and this is an important point to make, if I were to ask you to find the limit as x approaches 2, not from the left, not from the right, but 2, the only valid answer for that is does not exist, because negative infinity and positive infinity are different. They're not the same, so that's all you could do. But if you looked at a graph that was perhaps a different kind, that looked like this, such that the left-hand limit is positive infinity and the right-hand limit, let's say this is 3, the right-hand limit also says that you're going to infinity, then in this case, if this is the f function, the limit of this function would be infinity, because the left-hand side would be positive infinity, the right-hand side would be positive infinity. They agree, and so the answer is infinity. So what that tells me, if I don't have a plus or a minus as a superscript on that number here, if I don't have that, and I get an infinite answer, that means both sides are doing the same thing. If it's positive infinity, you're going up on both sides. If it's negative infinity, it's down on both sides. And so that's also graphical information, more information than D&E. D&E implies that they don't agree. Is one way to do these infinite limits. If I end up with a D&E, that means that one was negative infinity, the other one was positive infinity, most likely. And that's what we'll conclude from that. All right. So example 1, determine the limit of each function shown in figure 1.40 as x approaches 1 from the left and from the right. Okay, so looking at A, this is kind of like what we just talked about, so that's all right though. As we approach 1 from the left of this function, 1 over x minus 1 squared, so there's a specific example. Just kind of nice to know a specific one that does this. Looking at the graph, on the left side of 1, the graph is going up without bound, so that's positive infinity. And on the right side of 1, for that same function, looking at the graph is going up without bound, so that would be positive infinity. Okay. Then, if we were asked, this isn't what is asked, so let me put this in a different color. If we were asked to find the limit as x approaches 1 of this function, the answer would be positive infinity, because those two sides agree. Okay, now let's do graph B, the limit as x approaches 1 from the left of negative 1 over x minus 1. So on the left side, it looks like that one's going up, so that would be heading towards positive infinity. Then looking at x approaching 1 from the right side of that same function, if you look at the graph, it's going down without bounds, so that would be negative infinity. And parenthetically, what I would say is, if someone asked you what is the limit as x approaches 1 for negative 1 over x minus 1, because those two disagree, the best you could give me is that the limit doesn't exist. Okay. Okay, let's move on. Alrighty. So this leads us to the definition of a vertical asymptote. If the one-sided limit, and this is sufficient to have one side only, if a one-sided limit is infinity or negative infinity, that means that you have a vertical asymptote at that number that x is approaching from either the left or the right. Of course, you can have a vertical asymptote if you look at both sides, as we just did, but it's sufficient to look from one side only. If it goes to positive or negative infinity, then you will have a vertical asymptote. Okay, so, and I think I said this earlier as well, so let me repeat it because I think it's worth mentioning. If you have something that you've gotten in factored form, oops, it did not come out right. That in factored form is, I'm probably not going to make up the same thing, so I don't really care if it's not exactly the same. But if you have it in factored form, and there's something you can remove from the problem by canceling, like we can remove the x plus 2, the number that makes that factor equal to 0. So what would make x plus 2 equal 0? Negative 2. Because it's removed from the problem, that tells us that there's a removable discontinuity at x equals negative 2. And since the removable discontinuity is a point that's been removed, we can find its y-coordinate by substituting negative 2 into the reduced form of this, which would lead us to negative 1/5. This is close to what I made up last time, but not the same. I think it was x minus 2, x minus 2. Anyway, doesn't really matter. And anything still in the denominator that makes the denominator turn into 0 will be a vertical asymptote. And the vertical asymptote, since it's vertical, the equation of the line is x equals a number, and the number that is the location of this vertical asymptote is the number that makes the denominator equal to 0 after all the canceling has occurred. So in this case, x equals 3. Okay, so that's kind of a nice thing to recall from a pre-calculus perspective. And if someone said, hey, can you prove to me that there's a vertical asymptote at 3? And you certainly could. All you'd have to do is say, okay, well, let me look at it. As x approaches 3 from, I don't care which side you want to go with, because only one side is necessary. So let's go from the right. We're dividing 1 by almost 3, but bigger than 3, minus 3. So if we take something that's slightly bigger than 3 minus 3, the result is a tiny positive number. And if I divide 1 by a tiny positive number, I'll get a positive answer that's getting bigger and bigger and bigger the closer I get to 3 from the right-hand side. So that would be enough to say, prove that you have that vertical asymptote. Okay, so I've got a pre-calculus way of doing it like I started this example with, but if someone asks you to prove it, all you have to do is show that a one-sided limit as x approaches that value, in this case 3, is infinity or negative infinity, then you know you have one. All right, so let's see, what else do we have here? Okay, example 2, part A. Let's look at h of x, which is 1 over 2 times x plus 1. We can tell that when x is negative 1, the denominator is 0. And since I can't cancel x plus 1 with anything up in the numerator, I know that that's going to give me a vertical asymptote. So that means that I have a vertical asymptote at x equals -1. And you could graph this one on your graphing calculator and convince yourself that that's correct. Okay, so let's look at this one. H of x is x squared plus 1 divided by x squared minus 1. Well, we definitely want to factor everything we can to see if we can remove something from the problem and give us a removable discontinuity. Or if we can't remove anything, or once everything's removed, it can be, if there's still something in the denominator that makes me divide by 0, I'll have a vertical asymptote. Well, x squared plus 1 is prime. That can't be factored. X squared minus 1 factors to be x plus 1 times x minus 1. Nothing cancels. So in this particular case, I'll have vertical asymptotes at x equals -1 and at x equals 1. I know you may be tempted to write plus or minus 1 and kind of capture those in one statement, but I'd prefer that you not. I'd like for you to write the equation of each asymptote separately. So x equals -1 is one of the asymptotes, x equals 1 is another one. And if you'll sketch this one on your calculator, you'll see the two asymptotes and the behavior on either side. It's kind of an interesting looking graph. So every time I ask you to graph something on your calculator, I really do want you to do that so you can see how what we've talked about is verified and confirmed. Okay, C. Let h of x equal cotangent of x. Well, the quotient or ratio identity for cotangent of x says that that's the same thing as cosine x over sine of x. And we're interested in whatever makes the denominator be 0. So I'm going to solve the equation sine of x equals 0, and those are the numbers for x I cannot use. So if you find that, you're going to solve for that, and you should get multiples of pi. So 0, 1 pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi. All multiples of all integer multiples of pi are places where this function will have a vertical asymptote. So we will say the vertical asymptotes are at x equals multiples of pi, which makes graphing of this thing pretty easy. I'm going to graph this one for you by hand because you might not know how to graph cotangent on your calculator. You could graph cosine x divided by sine of x, by the way. You could do that and you would get the right answer. So I'm going to make a mark every pi over 2 on the x-axis, which is pretty standard for your normal trig functions. And on the y-axis, I'm going to number those by units, so by ones. And I've just figured out that there are vertical asymptotes at multiples of pi. So there's one at 0, one at pi, one at 2 pi, etc. We can keep going to the right if we want to. We'll do as many periods of this function as we want. There'll be one at negative pi and at negative 2 pi. So I've drawn a few of them that are relatively close to 0. Then this function is equal to 0 that is, you have a y value of 0 when the numerator is 0. And I believe we talked about this one recently. That happens at odd multiples of pi over 2. So I'm going to graph those x-intercepts, those zeros of the function. That's at 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc., etc. And then you might remember that cotangent is a function that decreases. You might also remember that at, say, pi over 4, cosine of pi over 4 and sine of pi over 4 are the same thing. They're both square root of 2 over 2, and that divides to be 1. So I can plot a point at pi over 4, 1. At 3 pi over 4, cosine is negative square root of 2 over 2, and sine is positive square root of 2 over 2. So that answer is negative 1. And the function looks like this. And I'm probably going to graph just 2 periods of this. Usually that's sufficient. So halfway there's a 0, 1/4 of the way there's a positive 1, 3/4 of the way there's a negative 1. And the graph looks like that. That's 2 periods of that graph. And you could keep going as many periods as you needed to graph. So there you go. It's pretty interesting. Okay, so let's turn to theorem 1.15. Which should make a lot of sense. I think it does make a lot of sense here. If C and L are real numbers, and the functions f and g be functions such that the limit of f of x as x approaches c is infinite, positive infinity, and the limit of g of x as x approaches c is finite, a real number L, then if you added or subtracted f of x plus or minus g of x as x approaches c, you'll have an infinitely large thing plus or minus a finite number. And if you have infinitely large and subtract 2 or add 7, you're still infinitely large. 2, the product. The limit as x approaches c of f of x times g of x will be a positive infinite thing times L. And if L is positive, it'll still be infinite, like 2 times infinity is still infinitely large. Or it'll be negative infinity if you multiply that infinity times a negative number. So if L is negative, infinity times negative 3 will be negative infinity. And if you have g of x over f of x as x approaches c, you'll have a constant over something that's getting infinitely large, like 2 divided by a billion or 2 divided by a trillion. That's getting closer and closer to 0. Replace all of those with one-sided limits and they're the same. And if f of x approaches negative infinity, you'll need to think that through in the same way, like the product. Negative times negative would be positive. Negative times positive would be negative. And so that kind of thing you need to think through. But those are limits, properties of limits that I'd like for you to know. So let's look at example 5 to see how that's going to be used. Part A, the limit as x approaches 0 of the constant 1 is that constant, and the limit as x approaches 0 of 1 over x squared. So you're dividing 1 by an extremely small number, because like 0.1 times 0.1 is 0.01. It's even smaller than the original number. Dividing a constant by something really close to 0 will give us an unbounded answer. And because positive divided by positive, because x squared is going to give you a positive result, this will be going towards positive infinity. Okay? So that means that the limit as x approaches 0 of the sum 1 plus 1 over x squared will be 1 plus infinity, which is still infinity. Okay. B. We're in this one asked to find the limit as x approaches 1 from the left of x squared plus 1 over cosine of pi x All right, so to do this, we're going to find the separate limits as x approaches 1 from the left of the numerator function. And since it's a polynomial, we can figure that correctly using substitution. 1 squared plus 1 is 2. And the limit as x approaches 1 from the left of the denominator function. Again, it's a trig function, so we can do this one by substitution unless it makes us divide by 0. So that'll be cosine of pi times 1. Pi times 1 is pi. The cosine of pi is -1. Oh, what am I saying? Pi x. Oh, it's cotangent. That's why I'm messing that up. Oh my goodness. I'm so sorry. It helps if you read things carefully. That's a cotangent. So let me go back and change that to a t. What I said was right. It just wasn't the problem they asked us to do. So my apologies. Get this set back up how I want it. So that should have been cotangent of pi x, cotangent of pi x. And there is no cotangent of pi, so maybe I need to erase. Well, the idea is correct. I'll leave it alone. There is no cotangent of pi. So if you'll look at the graph over there to the right and above, at pi, if we're approaching 1 from the left, we're going to have numbers pi times like 0.9, which is less than pi. At pi, this graph from the left side is going towards -infinity, right? Right here. So I need to erase part of my answer again because that's wrong. It's not -1. Okay. And that cotangent of pi isn't correct, but I'm going to make it sort of okay as a thought process if I say I'm approaching pi from below pi. And that is -infinity. All right, so going back up here to this question, this is going to be kind of like, I'm going to put this in parentheses, kind of like taking the answer for the numerator 2 and dividing it by -infinity. And if you take 2 and divide it by -1,000,000,000, that's very close to 0. So that'll head towards 0. Sorry I missed that cotangent and called it cosine because that was unfortunate. Kind of gave me a few minutes off to the side that I really shouldn't have done. Okay, so let's do the limit as x approaches 0 from the right of 3 cotangent of x. Of course, the limit of the constant part of that is the constant 3, and the limit as x approaches 0 from the right of cotangent x. And this is what I would have done above instead of writing that cotangent of pi from the left. That's not what I usually want to do. So look at the graph of cotangent we did. We're approaching 0 from the right side. So we're getting closer and closer to 0 from the right side of 0, and that's heading towards +infinity. Okay, let's go back down here, and that's +infinity. And so this limit, we'll be thinking in our heads, we're going to take the constant +3 and multiply it by something that's infinitely large, and that's still going to be infinitely large. Okay, now D. The limit as x approaches 0 from the left of x squared plus 1 over x. So let's look at those individual pieces of this problem. X squared, since that's a polynomial, we can do that by substitution. 0 squared is 0. Then, as x approaches 0 from the left, the limit of 1 over x. Okay, so we're below 0. We have negative numbers, and it's pretty close to 0. So positive 1 divided by a negative is definitely a negative number. And if we divide 1 by something really close to 0, the answers are getting bigger, so this becomes negative infinity. So what we'll be thinking here is this limit will be 0 plus negative infinity, which is negative infinity. Okay, that ends this section. We'll see you in class.